Hey everybody, Dave Lindbergh in Hong Kong, as always, with another episode of THD Podcast. And today, Simon, as always, calling in from Sendai, Japan. How's everything shaping up in Japan, Simon?
Looking really good here, Dave, in the run-up to Christmas, although this is actually a not time-accurate release, so I shouldn't have said that. Get on with it.
Yeah, don't worry about it. And so calling in from Graz, Austria today, a couple guys from USound, Paul Kutschera, the VP of Sales, and Mr. Konstantin Davy, Field Application Engineer at USound in Graz, Austria. How's it going today, gentlemen?
All good. Thank you, David. Thank you, Simon.
Okay. So, yeah, I think a lot of people building, headphones and different kind of notebooks, tablets, phones, all kinds of stuff. They've heard a bit about USound in terms of these MEMS speakers that are kind of like making waves, not to be cliche in audio speak, but they're kind of making some moves in the market. And I'm sure a lot of people understand what a MEMS microphone is, but the MEMS speaker. So I guess what we want to find out today is a bit about, how long has USound been in business and how did that come to be? And what kind of products are you guys building your MEMS speakers into? So maybe talk about where the company comes from a bit first, and then we can dive into the technical.
Great. Thank you for the chance, David. So USound itself was incorporated in 2014. The whole idea started a couple of years earlier when our three founders worked together. From the principle, as you mentioned, it MEMS microphones are in the market for a couple of decade basically now. But on the speaker level, we are still working on the principle that was developed over 100 years ago. And our founders made the decision 2012, 2013 that it is time for a change. I can show you some slides of our company presentation. I'm just going to start that right now.
Mm-hmm.
Let me know once you see the presentation.
Yeah.
Yep. Got it.
Okay. So as said, we're USound, and we're the first company that has industrialized and commercialized MEMS speakers. As said, we were incorporated in 2014 in our headquarters here in Graz, in Austria. Graz, the second largest city in Austria. And we were quite lucky in the beginning and collected roughly 17 million euros in venture capital from local venture capitalists. And of course, also public funding. And from the very beginning, we had a focus on our patent family. So from the beginning, we filled around 29 patents and started partnerships with international manufacturing companies. So we do not have our own production because building up a semiconductor plant nowadays will definitely cost you more than 17 million euros. So we partnered up with STM, Flex, formerly Flextronics in Althofen, as well as a well-known PCB manufacturer called AT&S, which is just 40 kilometers away from our headquarters. And those guys are providing building the MEMS speakers for us. We won a couple of awards. 2007, the Austrian-born Global Champion, which is a local startup award, as well as Fast Forward Award, also some local awards here. And in 2018, we started a partnership with 3Note, who are currently also producing our B2C product, which we will show you a little bit later on. And in 2018, we also started the mass production on wafer level with the partners I've mentioned before. In 2018, we grew the patent family, so it's a little bit over 150 patents pending right now, and we grew. So we also had by then already the office in Vienna, where Konstantin is sitting right now, where our R&D is located, but also our office in San Francisco, which is unfortunately due to Corona idle at the moment. but we will hopefully be able to staff that soon. And we also have an office in Shenzhen, where two of our colleagues, an account manager and a field application engineer, his name is Konstantin, is taking care of the greater China market. And 2020 was then the year of our first B2C product. We basically saw in the development of our reference designs that we have the capabilities to bring our own audio classes on the market. It contains two MEMS speakers, a woofer, and a microphone. And I'll show you some pictures after.
Hey, Paul, B2C
yes.
being what's B2C acronym?
Business to customer. So okay, we have two lines. Direct sales to end customers. This is where Fauna is, and where when you look at the management group here, where Christopher Butcher is responsible. So he's taking care of the B2C market, while I'm taking care of the B2B market, dealing directly with the customers.
Paul, just a follow-up question to Simon. Would you say strategically, was that meant to seed the market with getting some finished product out there to? Because often people with a whole new concept, they don't know where to put the technology. But if you show them, everybody goes, okay, yeah, we need to do that as well.
Exactly. So it's a two-way strategy here. On the one hand, we knew that we can do it, and that there is a demand for audio classes in the market. And as you said, it's of course also a demonstrator. It's a physical product we can bring to our clients who are developing virtual reality or augmented reality devices, and they have something in their hands. They can test, they can hear the sound, and they can make a decision based on that.
Okay.
So as mentioned, these are our founders, Ferruccio, Jörg, and Andrea. They worked together, they came up with the idea 2012, 2013, and then incorporated the company in 2014. Quite quickly, a little bit about the partners. I mentioned that we're a fabless company. We're working with STM, Flex, AT&S, 3Note, TDK. But we have already also distributors. So we're working with DigiKey, who are selling the development boards, the reference designs, and of course the MEMS speakers, as well as other distributors taking care of different regional markets. Mm-hmm. So a little bit about the technology principle. Konstantin, please.
All right. So I'm assuming that you all know how a traditional moving coil loudspeaker works, and you also know how a balanced amateur loudspeaker works. How is a MEMS loudspeaker different? Well, MEMS loudspeaker uses an entirely different principle of motor actuation. You might also have heard about piezo loudspeakers, those piezo discs that move.
Yep.
We're typically used as tweeters. Although ours are too based on the piezoelectric principle, they don't actually have a lot in common with traditional piezoelectric loudspeakers. So even though they work on piezoelectricity, you cannot put them into the same label because they have different driving requirements, different performance. So it's not the same. Just as a reminder how piezoelectricity works, a piezoelectric crystal can shift or can change its shape depending on the voltage that you apply to it. So if you have a piezoelectric cantilever, you can apply voltage to it and make a structure move up and down. This is the essential working principle of a MEMS loudspeaker, the one that we use. By using multiple cantilevers, we can move a central mass, which we call a piston. We can move that up and down. And there we have up and down movement, just as in a traditional loudspeaker, except that this structure is entirely made with MEMS processors. So it's a lot thinner, a lot more precise to make. The only downside of this is that, I'm not done yet. The only downside of this is that MEMS elements get more expensive the larger they get. So it's then the reason to keep the MEMS elements small. The downside of having a small loudspeaker, of course, is that there's not enough diaphragm area. So what we did is we have a hybrid approach where we add a traditional acoustic diaphragm on top of this MEMS structure, which actually creates a sound. And this diaphragm is moved by the MEMS structure. So from the outside, it looks like a traditional loudspeaker, except that the motor structure is not a moving coil and a magnet, but it's a MEMS element.
Okay.
And so that's actually a layer of crystalline structure that's giving you the piezoelectric effect, let's say.
Sort of, yeah. This is the MEMS element. This is essentially a silicon part with piezoelectric crystals on it that allows it to move. Yeah.
So that part of it is actually generated as part of a silicon wafer directly.
Absolutely. We get the wafers from the foundry, and on top of the wafers, we just put the diaphragm essentially put it all into a package with the connection points, and this is essentially the loudspeaker. Yeah.
Beautiful.
So this is how a MEMS loudspeaker works. But what makes a MEMS loudspeaker different to a traditional loudspeaker in terms of how to use it or what benefits does it give you? The most obvious benefit is the size. A coil has a certain minimum thickness. A magnet has a certain minimum thickness. They all have a certain minimum size, which limits the performance. This, in some way, too applies to MEMS loudspeakers, except that the minimum size that we can achieve with silicon processes is, point something millimeters. In fact, our current loudspeakers are 1.6 millimeters thin, and the next generation that we're working on right now aims to have a thickness of less than 1 millimeter.
So your actual moving element, I keep calling it the piezo part. What should you call it? What should I be calling it?
We call it the MEMS.
Okay, the MEMS. The MEMS part of
microelectronic
is would be very tiny then, would it?
Yeah. The surface area of the MEMS is a few square millimeters.
Mm-hmm.
But the thickness of the MEMS part is, it's silicon. It's essentially nothing.
Yeah.
The thing that creates the thickness is the packaging around it, which is there to protect the diaphragm, to offer the connection points, which can be made much thinner because we don't have the limiting size of the magnet that we have to keep.
Mm-hmm.
So in the end, MEMS speakers are a lot thinner. They're also obviously a lot lighter than traditional loudspeakers because there is no magnet, and the magnet is the driving mass behind it, and we don't have a magnet, so they're much thinner. Another benefit is, since we use silicon processes, we can make a loudspeaker that you can use with reflow soldering, which streamlines production processes for the end product a lot, because you don't have to hand pick the loudspeaker and hand solder it. You can actually use traditional reflow soldering stations, which enables you to use fully automatic assembly. MEMS loudspeakers also have a benefit inherently to their transducer principle, because the MEMS technology or the piezoelectric technology actually gets slightly more efficient towards high frequencies. So it is absolutely no problem to reach a high-res audio certification with a MEMS loudspeaker. They can easily reach up to 40 kilohertz, even higher than that if need be. We're actually working on specific versions of our MEMS loudspeakers that are targeted just for the ultrasonic application. They use the same technology, just a different form factor to benefit of the ultrasonic performance. So we're making versions of our MEMS loudspeakers that are just working the ultrasonic region, because we do have some applications in that as well. And the last benefit of
the total mass of the moving elements would then be incredibly low. They take away the diaphragm, and
exactly.
So in traditional speak, you have the mass of a coil of wire. Essentially, you can't get away from that.
Correct. This is also a benefit. We don't essentially have a moving mass. We have our moving mass is comprised of the diaphragm and a piece of silicon. Silicon, since it's essentially thin, I'm just going to say thin.
Yeah.
Since it's thin, it weighs essentially nothing. So the driving force of what creates the mass is essentially the diaphragm construction.
Yep.
We do have some stiffening of the diaphragm, which determines the mass in the end. But yeah, it's a lot lighter than having to use the same diaphragm but using a voice coil on top of it.
Yeah.
And lastly, the big benefit of using silicon processes is that you can have the same extremely tight tolerances of silicon processing. Silicon manufacturing silicon foundries are set up to have extremely tight tolerances, because they're working with tight dimensions all the time. So it's in the end we get a much lower part-to-part variation from one loudspeaker to another, because we can use silicon processing with much lower or much smaller tolerances.
Mm-hmm.
So this is this is what the current MEMS loudspeaker actually looks like. Our current family of loudspeakers, we call it the Ganymede family. They have two variants. So we have made two variants of our MEMS loudspeaker, one being optimized towards maximum acceleration and the other being optimized towards maximum excursion. Just as a reminder, if you want maximum SPL output and you're playing in free field conditions, maximum SPL means you have to achieve maximum acceleration. Whereas if you're playing in occluded ear conditions, then you, in order to reach maximum SPL, you need maximum excursion. So this is why we developed two different optimizations of our MEMS. The loudspeakers themselves, they look identical from the outside. The difference is really just with the MEMS geometry. So we have two versions of our Ganymede family. The first version, which we call ADAP, which is the one we see right here. This is the one that we use in free field applications. So it is optimized towards maximum acceleration. We reach a sound pressure level of roughly 70, 71 decibel. This is measured in buffer conditions at 10 centimeter of distance, with a resonance frequency of roughly 3 kilohertz, 2.9. So it's essentially a plateau over 3 kilohertz and falls off at 12 dB per octave below. One thing to note is that electrically speaking, the MEMS loudspeaker behaves as a capacitive load. So it has different requirements to the amplifier. Since its impedance is essentially that of a capacitor, there is no mechanical influence on the impedance. So the impedance, if you look at just the impedance, it is indistinguishable from a 38 nanofarad capacitor. This means that the impedance is relatively high, much higher than traditional loudspeakers, so that the voltage that you need to drive the loudspeaker is also higher by about an order of magnitude. We have typically a maximum voltage level of 15 volt peak. This sounds like a lot, but remember that the impedance is also extremely high. So the current flowing through it is actually almost negligible. So the total power consumption is absolutely nothing out of the ordinary. It's very comparable to traditional loudspeakers, smaller than most of them actually. Yeah, we also see the size. The size of the loudspeaker that we currently produce is 6.7 by 4.7 by just below 1.6 millimeter. Yeah, the picture that we see here is the version for maximum excursion, which we use for occluded ear applications. As you see, it looks the same from the outside. The difference is really just in the MEMS structure, which you don't see in this picture. For this version, which is optimized for maximum excursion, this we measure in coupler conditions to simulate the occluded ear application. This version has a resonance frequency that is slightly lower. That is at 2.7 kilohertz, and we reach an SPL of roughly an SPL plateau of 116 dB. It rises slightly towards 1 kilohertz, and then of course there's the coupler resonance at 11K.
Right.
Yeah, so 116 dB is reached at 15 volt peak. Also, as a reminder to how the piezoelectric principle works, is you do need a bias voltage. In this case, we need a bias voltage of 15 volt DC. So this is it has different requirements to the amplifier as traditional loudspeakers. There are off-the-shelf components that can deliver this, and we also developed our own amplifier for this, which we will get to in a second.
Do you mind a quick sidetrack into what is, I didn't know about this, what is the bias voltage needed for?
So the piezoelectric material that we use can only contract. So if you wanted to move up and down, you first need to contract it and then move it up and down.
Okay, so imagine it's like a single supply op-amp kind of thing. You have to bias to halfway. Correct. You can't go negative.
Yeah.
Beautiful.
Because that's essentially it.
Okay. The question now is, of course, where can we use the MEMS speakers? So we have defined certain applications where we see also our products. Most prominent, of course, in-ear headphones and 3D headsets. Everything you can either plug into your ear or put over it. So this is the whole gaming industry, but as well as the communication industry, headsets, as all of us are wearing it right now, in earbuds, hearing aids, as well as audio classes. This is the whole family of virtual reality, augmented reality classes, or audio classes, which we have, as said, also developed on our own. We do see our products as well as in industrial automotive applications, test equipment, proximity sensoring, which is the latest series, which Konstantin will explain a little bit later. But we have also built our own hi-fi loudspeakers, which we will show you, in a minute. In order to test the MEMS speakers, since it's not a traditional speaker, we've come up with reference designs, which we produce in small quantities, which are. Or the idea behind this is to show something to our clients and let them experience the sound and the possibilities they have on both on a sound level as well as on a design level with the MEMS speakers.
So Paul already said we don't typically sell directly to customers aside from our Fauna project, but we do make reference designs, which makes it easier for business customers to use our loudspeakers in their products. One of the reference designs that we did is the Dione Soundstripe, as we call it. The idea behind it is to take the idea of an LED stripe, as a stripe of LED lights, but bring it into acoustics. This is why we always refer to our loudspeakers as the LED of acoustics, because it has the same influence on the acoustic industry as the LED had on the lighting industry. What we did with the Soundstripe is to have a flex PCB, so it behaves like a strip of cloth. You can move it, you can bend it, you can flex it in all directions, and there's multiple MEMS loudspeakers placed on that PCB, each coming with their own back volume. So in the end, you have acoustically speaking, you have a tweeter that acts as a tweeter, but mechanically speaking, you have something that can be shaped directly to the shape of your industrial design. So it allows you to use much more non-traditional shapes of a loudspeaker. It can be shapes of just a traditional loudspeaker in a different shape, which we have a more detailed reference about that later. But it can also be something like if you have a coffee machine that you for some reason want to have it talk to you, but you don't really have the space for a traditional big loudspeaker setup, you can hide the woofer somewhere inside and then add the tweeter in a place where it doesn't take up a lot of space, which makes it a lot easier on the industrial designer. Proteus is our project where we develop more traditional looking loudspeakers. Proteus 1.0 is a very traditional loudspeaker. Again, this is not something that we sell to customers. This is a reference design. Although we do sell Proteus 1 as a DIY kit, so you can build it yourselves if somebody's interested in that. Proteus 1 is a very traditional two-way loudspeaker with an 8-inch woofer and 40 of our MEMS loudspeakers in an array with a horn in front of it to shape their activity pattern. This is to showcase that a MEMS loudspeaker can not only be used in traditional micro loudspeaker applications, but also can also be used to form a very traditional-ish loudspeaker. We use those, for example, in our meeting rooms. Proteus 2.0 is where we took it up a notch to really showcase the flexibility of industrial designers when they're not bound to using traditional shapes for loudspeakers. Because with a traditional speaker, you're bound to have something where the tweeter fits into, and it does take up a lot of space in the end. By using a Dione Soundstripe, you have much more flexibility. We hired an industrial designer to come up with something that is it's more a statue than it is a loudspeaker. And then we retrofitted a loudspeaker inside. So we had this gray box in the bottom where the woofer is, a 6 centimeter woofer. And then we added in those 3 big metal tubes, they're about 1 centimeter diameter. We added an array of our micro loudspeakers. So in the end, while it doesn't look like a loudspeaker, it acts like a loudspeaker radiating in 360 degrees. So it is a very nice looking decorative loudspeaker that doesn't look like a traditional loudspeaker. And this is only possible because the loudspeakers themselves, the transducers, are so small that the industrial designer has much more freedom.
Beautiful.
Yeah, so another big thing for us, another big project is the application of eyewear in any sense. It can be AR, it can be VR, or just simple Bluetooth glasses with loudspeakers inside. A lot of the time, companies who develop those glasses have some experience with electronic products. Some have experience with fashion glasses, but very few of them actually have experience with acoustics. And this is where we offer a design service where we design the acoustic module that contains the loudspeakers, can also contain the amplifiers and electronics necessary to drive it. And then we sell this module directly to the business customer, which they then put into their product and then sell it as theirs. So they don't have to worry about measuring and verifying the acoustic part of it. We can do that for them. All of those we typically design directly to the ID of the customer, but just to showcase what this might look like, or especially what it might sound like. What we do sell is this. We call it Danube 5.0, which is just a demonstrator that has a box with loudspeakers inside, which you can place onto glasses, so that you can hear what the end product would look like, even when the actual idea of the glasses is not finished yet. The idea behind that. You have a question?
Yeah, just are all these kind of prototypes available for developers to order? Or are all of them available to order?
Yes.
Okay.
Yes, everything we show so far can be ordered directly via us, as well as via DigiKey or the distributor, the regional distributors. Okay. And this information is actually all available on our homepage. So you can just reach out to both of us and let us know. Sure. Sorry, please continue.
Right. So what we did with Danube is the big problem when you add acoustics to something like an eyewear product is you have the decision between a small loudspeaker or a large loudspeaker, and then you have a trade-off between performance, power consumption, and just sound performance, sound quality. And we actually found that we can get the best compromise, both in terms of power consumption and in terms of taking up space, by using a two-way system. This might sound strange because two loudspeakers are more than one loudspeaker, but two loudspeakers actually perform better than a single small loudspeaker, and they take up less space than a single large loudspeaker. So this is why we use a two-way system where we pair our MEMS tweeter with an electrodynamic woofer to form a two-way system with a crossover point at roughly 2 kilohertz. Depends on the exact ID, because the ID will affect the high frequency performance, so the crossover point will slightly change. What we also implemented here is directionality. So acoustically, this performs as a dipole, so that the sound is only radiated from the point of the loudspeakers down into your ear, but not to the front, to the back, and to the side. So the person standing next to you doesn't hear anything, or hears a lot less from whatever content you're listening to than it would if it was a monopole configuration. It's a little more tricky than that. There's a little simulation also going on to improve the directivity. This is something that we have actually patented to form a directivity control in the application of an eyewear product. Yeah, this is how it looks in more detail. The piece on the left that you see is the actual acoustic module, and the rest is just the mounting points. So you can mount it as a demonstrator. You can change the position. Like I said, it's a two-way system to improve the bandwidth. We can easily reach 20 kilohertz. It's the best compromise to reach high SPL while still having a small space consumption. Has a dipole configuration and acoustic design to increase we call it the audio privacy, as in the person standing next to you doesn't hear what you're listening to. Yeah, that's essentially it.
The bottom end 300 hertz, is that a 3 dB down point? How do you get that figure?
It's since it's so close to the ear, it doesn't exactly behave as nicely as in a traditional free field setup where you have the cutoff point and then it goes down predictably. Yeah. It's a little more complicated because it's a more gradual slope.
Right.
And it also changes depending on the requirements of the customer. Some customers do have a few cubic millimeters more space available, so we might put a slightly larger woofer inside so we can shift it down a bit. We have reached 100 hertz as well.
Yeah.
300 hertz is just the standard model that we choose if no other recommendations are made by the customer. If there is very, very little space constraints, then we can use a very large woofer and reach even lower. If the space constraints are extremely tight, then we might use an even smaller woofer, which has the downside of maybe increasing the low frequency cutoff to 500 hertz or something like that.
Yeah.
This is something that we're very flexible on.
Okay.
Yeah, and out of this whole development process we had, the idea was born to create our own audio classes, because we saw, as said, there's a demand on the market, and that we have the capabilities of actually producing a fully functional audio class. And this was done in 2020. It's called Fauna. It's a subsidiary of USound. And what you see here is the actual product, with the MEMS speakers mounted in the ED woofer mounted in the temples, with some touch controls where you can adjust the volume. You can pair it with the Bluetooth pairing. You can activate your voice assistant like Siri. Can be equipped with any optic, so you can just go to your optician and get your prescription glasses in. For those who don't wear glasses, these are available in sunglass versions, or what I'm using, the blue filter version, when I'm having 10 calls a day and actually working on the computer. It filters out the blue light of your monitor, which is quite nice, actually. Quite nice too. Yeah.
I was just gonna say, Paul, you said off the record that you lived in Hong Kong, so maybe some of the girls that wear the glasses without the lenses, you could do that as well.
Exactly, and they still can take your phone calls, which is quite nice and hand free.
Yeah.
So yeah, this was launched in October this year. So we've shipped now the first couple of thousand pieces already. Mass production is fully running. The Fauna itself comes with the charging case, which is on the sides. You have the electrodes and then actually charging the whole thing. Battery life is around 4 hours, depending on the usage. And the case itself can recharge the glasses up to 4 times. So even if you're on the go, you can quickly recharge the glasses and use it. So this is definitely something we are very, very proud of, that we've brought that in the market, and we really see a high demand on those things.
Awesome.
Then, as said, we have also reference design for headphones and earphones. Again, those are not available for, or not intended for mass production, but rather as a demonstrator for our B2B clients. And Konstantin, please.
Yeah. So Tagete is a slightly different product that doesn't have anything to do with MEMS loudspeakers themselves, but it is only possible to do with MEMS loudspeakers. And I'll get to why in a second. So I'm going to assume that you know how surround sound simulation works. I'll just skip over the basics.
Yep.
In a traditional surround sound setup, you have at least 6 loudspeakers, 5.1 or 7.1 or even more, depending on which exact format you use. And you create the impression that sound is coming from in front of you by having the loudspeaker in front of you play the sound. You create the impression that sound is coming from above by having a loudspeaker coming from above. Simulating this for headphones, to have a surround sound headphone, is typically done by having a single loudspeaker per side. But by simulating the influence of the HRTF of your ear, so the way that your ear affects the sound field, having this effect simulated, and then having the final sound, so the sound that you want to play, plus the effect of the HRTF added on top of that, playing this through the one loudspeaker that you have, which in theory works perfectly fine. And if you have an average ear or an ear that fits the ear used for the simulation, then this works perfectly fine. Unfortunately, I myself do not have an average ear, and I'm assuming that none of you do, because if we look at the numbers, then most people actually don't have an average ear, because almost every human ear is different, almost in the sense of how fingerprints are different. So while in theory an HRTF simulation works perfectly fine, in reality it works for almost nobody. Mm-hmm. So we thought we could improve upon this concept by taking the biggest variable, namely the shape of the pinna, out of the equation. Simulating the effect of simulating the effect of the head and of the shoulders is relatively simple because those are relatively the same for all persons. Not saying that the shape of the head is the same for every person, but the acoustic influence of the head is very, very similar on every person. So there's not a lot of variation of that. The biggest variation of the HRTF is created by the PRTF, by the pinna-related transfer function, so the exact shape of your ear. And this is very different for everybody. So what we chose to do is, how we tackled this problem is by simulating the influence of the head and of the shoulders, but not simulating the influence of the pinna. And instead of simulating the influence of the pinna, we actually place small loudspeakers in front of the pinna, above the pinna, behind the pinna, below the pinna, around the pinna. All of this is just a very complicated way of saying we don't simulate surround sound, we actually play sound coming from the direction that you want it to come from. This concept is not novel at all. There have been some headphones attempting to do that with traditional loudspeaker setups. You might remember them, they were not particularly successful, mostly due to their weight, because they used, well, at least 4 loudspeakers per side, which can get very heavy if you use traditional headphone loudspeakers. Using MEMS loudspeakers, which are extremely light and extremely small, this becomes a lot easier to do because you can use a simple woofer for low frequencies and pair it with, for example, we use 16 MEMS loudspeakers around the ear. And it still is a very lightweight headphone. It's even lighter than traditional headphones because of the open ear cup that we used. And you have a surround sound headphone.
Beautiful.
Yeah, all the processing is done.
The processing. That's what I was going to say. The processing.
Yeah, the processing is all done on the headphone. It connects with a simple USB-C interface to the computer. Can simulate 5.1, 7.1, other audio formats. And in essence, you have a surround sound headphone where, from the perspective of the user, you don't have to do anything other than plug the headphone in with USB-C. It addresses the computer, or it is addressed from the computer as a surround sound system, and all the processing is done directly on the headphone.
So you got 16 MEMS mics. Are they driven in groups of 4 or something like that? Is it?
Correct. Yeah. This is what we used for this specific version. Another reference design that we have is the traditional application of an occluded ear application is a traditional earbud. This is just to showcase how does a MEMS loudspeaker sound when you use it in a traditional earphone. This could be a true wireless earphone, could be a wired earphone. Just for the sake of simpler and quicker development, we developed a USB-C earphone, which we based on our MEMS loudspeaker Achelos. Just a reminder, Achelos is the version of Ganymede that is optimized for maximum excursion, meaning maximum SPL in occluded ear application. It's a USB-C earphone with a DSP in the clip box, which also contains all the driving electronics. Has just a single MEMS loudspeaker that drives the full range from 20 hertz to 20 kilohertz. Actually, it reaches below 20 hertz. And it could reach above 20 kilohertz depending on what sample rate you set your system to, because it connects via USB-C. Yeah, it's very lightweight. Also, due to the fact that the MEMS loudspeakers have relatively high impedance, the influence of the cable on the sound, the impedance of the cable becomes less and less important. So you can actually use a lot more different cables, and you don't have to use the one with the highest conductivity. We have a prototype where the cable is essentially just a piece of string with a few metal parts in it. It has a relatively high impedance for a cable, but still lower than the loudspeaker. So even though it just looks like a piece of cloth, it conducts enough electricity to drive the loudspeakers, and it doesn't actually have any influence on the sound.
Oh. Yeah, that could be very interesting. I've seen some kind of people trying to incorporate speakers or technology into sporting wear or textiles. So if you can run really thin, flexible, conductive fiber that is enough to drive that, then that's cool.
This is one of the applications that we're also working on. I don't think we're showing this in this presentation, but we do have it's in the pre-stages of a reference design, but essentially it's a curtain with loudspeakers sewn into it and driven by some of this textile being conducted. Yeah.
Cool.
Yeah.
So those were the reference designs. If you want to play around with the MEMS speakers on your own and actually test it, we also provide evaluation and development boards. The intention here is that any acoustic team in a company can actually get that quite easily and use it for rapid prototyping.
Yeah, our main development board is what we call the Helical board. It's a development kit that has all the electronics necessary to drive a MEMS loudspeaker. As a reminder, it has different requirements for the amplifier due to the load being mostly capacitive, and also needing a 15-volt DC voltage boost. All of those electronics are included on the board. It connects to the PC. It either can work standalone as a USB-C device or a USB device. It can also work in conjunction with the Raspberry Pi platform with a 40-pin GPIO interface. It contains sufficient amplifiers to drive 2 MEMS loudspeakers and also 2 electrodynamic loudspeakers. So if you want to work on a two-way system, most prominent example being our audio glasses, which we typically develop as two-way systems, then you can use Helical as a development kit to drive those. Mm-hmm. It's all available on DigiKey, by the way.
Where did the names of your products come from? Is it Greek or where? Somebody.
They are partly Greek, yeah, but not. We don't choose it because they're Greek. We choose them because they're the names of stellar bodies. So the first project that we worked on was Moon, and so the Moon of Earth. And then for every product or every project that we have, not necessarily just products. Every project that we have, it might just be a development project. It might be the project of setting up a new lab. All of those projects get the names of different stellar bodies.
Ah, that's cool. That's cool. I once worked for a company and named all their prototypes after Bond girls.
That's a nice idea too.
That's a nice idea.
It does sometimes make the names a little hard to pronounce, like Amalfia.
Yes,
that took me a while to learn. Amalfia is a simpler version of Helical. It's essentially just a linear amplifier to drive our USound MEMS loudspeakers. It can drive multiple loudspeakers at once, connected in parallel. It can drive them up to 80 kilohertz. This is a product that we typically sell for people who just want to try out a MEMS loudspeaker without any of the additional fuzz, no filters, no nothing, just be able to test one MEMS loudspeaker and don't have an amplifier ready that can drive a capacitive load. So this is why we developed a very simple amplifier. We typically sell this together with what we call Carme. Carme is a very simple speaker box. You see that on the left here. It's a very, very simple speaker box containing one loudspeaker that you can connect to the amplifier just to do a very quick couple of free field measurements. It's also available in DigiKey. Yeah, and this is something that's a short outlook on what the future will hold for USound. The speakers that we currently produce and sell are the Ganymede family, which are rectangular loudspeakers. What we're working on right now is a round loudspeaker. This is partly because people are a bit reluctant to look at loudspeakers that aren't round, because most people, when they think of a loudspeaker, they think of something round. So acoustically speaking, this is not a problem to do a round loudspeaker. It's also from the perspective of the MEMS design, it's absolutely possible. So we went ahead, and for the second generation of MEMS loudspeakers, we developed a round one. This has a 10 millimeter diameter. The thickness is reduced to 1.45 millimeters. And this one is also waterproof. So if you want to do a product with certain IPX certification, the loudspeaker will not be the limit of that, which for traditional setups, often the loudspeaker limits it to IPX5, IPX6 often, due to the diaphragm principles, which is something that we were able to solve. So this loudspeaker is actually IPX8 waterproof on a component level. Mm-hmm. Yeah, it reaches, we can submerge it. We tested it with submersion up to 3 meters for 30 minutes. So yeah, water submersion is not a problem. This is slightly larger than the loudspeaker that we currently use, which increases the diaphragm area and increases the performance. It's also the MEMS itself has a different geometry and is also improved a bit. So this one reaches easily 120, 121 decibel on the plateau, and then high frequency performance. It's also reflow compatible. So yeah. Another thing that's coming in the future that we're working on right now is our project Himalaya, which is where we focused on the ultrasonic performance only. So these are not designed to play in the audible bandwidth. In fact, most of them have a frequency range that only starts in the ultrasonic range. I'm saying most of them because there are currently 3 types that we're developing with a resonance frequency of roughly 11 kilohertz, a resonance frequency of roughly 45 kilohertz, and a resonance frequency of roughly 90 kilohertz, with some bandwidth around that. Each targeted towards a specific ultrasonic applications where those frequency ranges are the ones that are typically used. Typical ultrasonic applications are obviously distance sensing, object sensing, proximity, gesture recognition. Then there's some how to say that in English? Some encoding going on where you can verify that two devices are next to each other by sending encoded messages in the ultrasonic band, which is an application, for example, for credit cards. Another thing that is possible to do with ultrasound is to form a parametric array. So essentially to create audio over ultrasound, where you play an ultrasonic carrier wave and then modulate the audio signal on top of that, and it gets demodulated only in the ear of the user. So you can have very precise directivity patterns where the sound only becomes audible at a very, very small sweet spot. An application for this would be, for example, to play audio in front of a painting in a museum, so that only the person standing in front of the painting would be able to hear the description of the painting. And this requires ultrasonic transducers, and this is what we're developing.
Very good for store applications, store display.
Yeah, exactly.
Correct, yeah. Exactly. Or think about automotive applications as well, especially for those of you who have kids. You would be able to play different songs or music depending on where you sit in the car. And whoever made a 5-hour trip to Italy with the little ones know what I'm talking about.
Okay.
Yeah.
Okay.
Another thing that,
yeah. Sorry. Go ahead.
Should we mention the haptics?
Yeah. Quite interesting concept as well, especially for virtual reality applications. You can actually create a force feedback on your hand with ultrasound. So when you think of VR applications, you're still working with controllers currently. But in theory, it's possible to skip the controllers and work with such an ultrasonic array that creates the buttons which you see in the VR just in front of you. And you could touch them and create also on your skin a force feedback, which would free up the virtual reality applications we see nowadays.
So you wouldn't just have your hand reach into air, but actually have some force pushing back against your hand and making you feel that, yes, I actually did push something right now. This is technology that another company has been working on, which we are supplying the transducers for. And I got to try out a prototype. It was eerie because you don't see anything, but you can touch something. It's still in the prototype phase, so it's not like you touch a piece of wood and you can distinguish it from touching a piece of metal, but you do feel something pushing against your hand, but you don't see anything, which is a very strange sensation because I wasn't wearing VR glasses at the time.
Wow.
Same for the parametric array. You don't have an idea where the sound is coming from. Just when you stand in that particular spot, it's forms.
Just there.
It's just there, yeah. Okay, that's it.
Okay.
From ours. Oh no, sorry, one more.
Oh yeah, we do have the Asic. So I already mentioned that the MEMS loudspeakers, being a capacitive load and having the requirement of a DC bias voltage, they don't work with traditional amplifiers, or at least not right out of the shelf. There are off-the-shelf components which, when you put them together, can deliver that, which is what we currently use in our reference designs. But for the future, we came up with the solution of designing our own ASIC, which would act as, on the basic level, act as the amplifier for our MEMS loudspeakers, but it can do a lot more. It also contains a DAC, so it contains a digital to analog converter, meaning that you can have a digital input and then drive the loudspeaker directly from that. It also contains a filter set, so you can add an equalizer to the loudspeaker directly on the level of the Asic. It also has measures of reducing the power consumption, because a capacitive load doesn't actually burn any of the energy, right? So there's no ohmic resistance. It's only a capacitive impedance, meaning that all the power is reactive. And if you use the right transducer principle, the right circuitry around it, you can, in essence, just have one package of power shifted back and forth from the amplifier to the loudspeaker, and printing your signal on top of it while not actually burning any energy. This requires, of course, a special amplifier, which is what we developed, and we've shown power reduction of 50 to 60%, even in the prototype stage. What this also allows us to do is to adapt for the nonlinearity of the loudspeaker. Every loudspeaker has some form of nonlinearity, mostly due to the diaphragm, because diaphragm does not have the same stiffness on the same level of excursion. And we can predict that by using a very simple model of the loudspeaker, putting it onto the DSP on this amplifier, and then correcting for this in real time. Not just in a feed forward loop, but also incorporating a feedback loop, where we use a sensing voltage from the loudspeaker, feed it back to the amplifier, and then adapt for the nonlinearity in real time. In essence, this just reduces power consumption. It reduces distortion of the loudspeakers when you pair it with this amplifier. This is something that we're working on right now. The samples should be available in Q1, and mass production should start, well, next year.
Okay. All right. So back to see all of us.
Okay.
All right. So Simon, you take some notes. You got some questions for us?
I sure do. This is a ton of info. This is incredible. So can you tell us something about the diaphragm, so it can tolerate reflow temperatures? How do you stick it to the actuator? How do you stick it to the motor?
A lot of this I cannot go into detail, because this is where our IP lies, because having a diaphragm that can be reflow soldered or can be waterproof and sticking it to silicon is actually quite tricky. Yeah, I don't think I can say a lot more than that.
Okay, then moving on.
Taking a reflow,
Let me bring it another way. Does it have a similar characteristic, behavioral characteristic as an electrodynamic speaker's diaphragm? So let's say used in the case of in-ear earphones, a true wireless stereo earbuds.
It's based on the same material, yeah.
Yep.
So it's not that different at all. It's just a slightly different material composition that allows us to withstand reflow soldering temperatures, and waterproof. Being waterproof is just a way of having a motor structure that can withstand some type of force, paired with a diaphragm that can restore its original shape.
So taking that application, let's say you had like about a 6.5 by 4.5 millimeter package, I think it was.
6.7 by 4.7, yeah.
Okay, in that package, the diaphragm's behavior is more or less, call it pistonic, right through the audio spectrum. Correct. Up to what level? Up to...
it's pistonic up in the ultrasonic region. We use a multi-layer diaphragm to essentially have pistonic motion far beyond the audio range, because the torsional stiffness and the I don't even know the English terms, the wobblings.
Yeah. A wobbling
are shifted. Yeah, they're shifted to the ultrasonic region.
Fantastic. So then it is, if you're designing an earphone, you're just treating it as the acoustic volumes are essentially it.
Yeah.
In terms of the response.
We do have the main mechanical resonance of the loudspeaker, obviously, because mechanical resonance, which is for the INI model, is at 2.7 kilohertz. But other than that, it's essentially resonance-free, other than, of course, the coupler resonance at 12.5 kilohertz.
Yeah, it's not... do you feel you know a lot more about this than me by the sounds of it? Do you think that the resonance frequency, like a free ear resonance, is not particularly relevant for those occluded ear?
Well, you do see it in every measurement. So whenever we go to a customer and we say, yeah, we have a loudspeaker that, due to its small size, doesn't have any resonances other than mechanical resonance, and then we show the frequency response graph with a large peak at 12.5K, they always say, hey, you promised us a resonance-free loudspeaker. Why is there a resonance? And then we have to explain that this is in fact the resonance of the coupler and not of the earphone. So if you measure it with the high-res coupler, then the resonance, of course, is much reduced.
Yeah. Okay. So let's say just again comparing to an electrodynamic electrodynamic driver, let's say an 8mm speaker, you put filter paper on the back and essentially kind of critically damp it would be roughly your goal. Are you doing a similar type of a thing?
We do have damping measures on the back of the loudspeaker to damp the mechanical resonance. Yeah, this is also something that we can adjust to change. We do have for one application we exchanged the damping mesh for a different type to get a different damping, not exactly critical, but slightly higher, because this is what was required from this customer in this case.
Slightly overdamped, you mean by higher?
Higher resonance peak, so underdamped.
Okay, underdamped. Oh, interesting. Yeah.
Because they required a peak at that frequency range, so we adjusted the manufacturing towards that.
Got it. And how about the linearity of the motor itself compared to a? So is it? It's got its own suspension. I mean, a voice coil in a magnet is unsuspended essentially. It's the diaphragm is providing.
In the micro loudspeaker case, those are typically the only suspension being the surround of the diaphragm.
Yeah.
In large loudspeakers, you also have the. Is it spider in English as well?
Spider, it is.
Yeah, the spider, which centers the voice coil. So you have two suspensions for MEMS loudspeakers. We have to work calculating with two suspensions because the MEMS itself is obviously connected to the rest.
Yep. So
it's two aspects of the KMS. One being the diaphragm, the other being the MEMS. Mm-hmm. The MEMS itself is extremely linear. This one thing that we do to improve this is to use. This is one of the reasons behind using the DC bias voltage, because when I say it can only contract in one direction, it can move in the other direction, but it will repolarize and become very nonlinear. So it's not that there is no sound coming out in the other direction. It's just it's not in the ideal level, which is why we use it with that.
So actually pushing it into the middle of its linear range in a sense.
We use it in the range where it's the best compromise between linearity and power consumption. Yeah. Mm-hmm. You can use it with a higher DC voltage, which does improve it slightly, but the point of diminishing returns is just below 15 volts, so we settled on that.
And so the figures that you quoted for maximum SPL sounded pretty high, getting up close to 115 dB, I think it was. Is that right?
That depends on the exact model with the Ganymede Achelos, so the occluded ear application of the rectangular loudspeaker. We reach a plateau of 116 dB at below 1K. With our current loudspeakers, with the circular loudspeaker, we reach 120, 121. This is something that we're still going to improve with MEMS design.
If you're implementing it into an over-the-air headphone, you bank a bunch of these together just to get a large surface area?
Yeah, but in over-ear headphones, we typically use the free field variant, so we only use them as tweeters. Mm-hmm. Because over-ear acoustics are very, very different from in-ear acoustics. Mm-hmm. So we cannot exactly make use of the occluded ear principle there.
Okay, yep. The occluded ear principle being that you have a completely sealed volume and its displacement that is the only thing that matters.
Yeah, exactly. Occluded ear principle being that the dimensions of the volume of air in front of the diaphragm are smaller than the wavelengths of sound that you're playing to, so that you don't have reflections, that the sound pressure level is the same in all of it. The same in all of the volume, so that the sound pressure level is determined by excursion, not by acceleration.
Interesting. And if you want to bank a lot of them together, do you just put them in parallel?
If you want to have them play in phase, then this is what we typically do. Yeah, just connect them in parallel, which of course requires an amplifier. An amplifier that can handle that. We do have applications not developed in-house, but where we're working with other companies that are developing it, and we're supplying the transducers to, where they're working with arrays where every loudspeaker is addressed separately, so that you can have all types of fancy stuff, beamforming, anything like
Years
that.
ago, I used to play with electrostatic speakers, and we used to use a huge transformer in order to deal with the capacitive load, and then use a standard amplifier. Could you tell us something about what the amplifier circuitry looks like?
I can't, because I'm an acoustic engineer, not an electronics engineer. But we did publish a paper on how to design amplifiers for MEMS loudspeakers. This is available on everywhere.
Yeah, we could put a link in the description.
Yeah, we can do that.
Is it a switching amplifier?
No, it's more complicated than that. It's essentially it's a new class of amplifier. We call it Class U.
Oh, good.
For USound.
Yeah.
So you know how a Class D amplifier works? Do you know how a Class J amplifier works?
No, I don't know that.
Where you have voltage that adjusts according to the input signal to reduce power consumption.
Similar to,
it works alongside that principle, but it's a little different.
Interesting. Okay then. And just in my mind, the killer application, because of what I'm into, would be true wireless earbuds with one board, with a voice feedback, a feed-forward microphone, soldered reflowed onto one side, the MEMS speaker onto the other in one shot, and you just drop that baby into the housing and you're done. Because soldering up the speaker wires is a kind of a horrible job in those things.
Yeah. And hand soldering also is difficult because you only have to slip a little to burn the housing, and then you can throw all of it away.
Yeah.
Whereas with reflow soldering, you just have to set tight enough tolerances.
And
true wireless ear headphones are one of the big applications where we do have the manufacturing partner 3Not that are doing essentially exactly that.
Yeah.
It's not exactly as simple as having a simple PCB with loudspeaker and the microphone and the SoC on top of it, because you do need the loudspeaker near the ear, or at least somewhere close enough. But this is usually solved with Flex PCB, where you have the loudspeaker and the rest, and then you just shape it in.
Yeah, mostly using Flex. Ooh, that's good stuff. That's so good. Take it away, Dave.
All right. That was quite a bit of information on MEMS speakers. So yeah, thanks, guys.
Can you tell us anything about the cost in a real production application?
In
the order of?
Not in the order of let's say $2.5 to $6 depending on quantity.
Okay, so I'm looking at public information. I'm just looking at DigiKey on the side. They've got 1,000 yen for one piece, so that's about $10.
Yeah,
for one off DigiKey. So I guess that would be like I would guess that'd be like $2 in volume kind of thing.
Yeah.
I think the economies of scale might be pretty good using
using a semiconductor process. That's the whole idea. The moment, of course, someone is ordering millions of speakers, this will drop down immediately.
Well, I don't know. Even if you've got a brand and a story to go along with it, $4 on speakers is not the end of the world if you can sell your earbuds for the price.
Yeah, exactly. If you look at balanced amateur loudspeakers that are selling for 30, I've seen some for $50 a piece. Even if you order them in high quantities, they still go down from 40 maybe down to 30 for the high quality ones. So having a $4 or a $2 or a $1 MEMS loudspeaker is a lot cheaper than a BA loudspeaker.
Yeah, that's awesome.
While not sacrificing any performance.
Yep. And can you say claim any superiority in performance? Do you think?
Well, if you
take the angle about the consistency, would you?
Mm-hmm.
You take the
angle. Of course, the
consistency
is one of the big aspects. Yeah. Another big aspect is if you try to design an earphone with balanced amateur loudspeakers, there are ways that you can make an earphone with a single BA loudspeaker, but it's tricky and it has limitations. The only successful model that I'm aware of is, of course, the Automotic ER4, which is fine, but does have limitations. Typically, if you want to design an earphone with a balanced amateur loudspeaker and you want to design it specifically towards your target curve, then you're going to have to use multiple BA loudspeakers because the ones optimized for low frequencies cannot be used at high frequencies due to the extremely high inductance. The ones optimized for high frequency, they don't really have any noteworthy low frequency output due to the small front volume. So what you typically do is you have a multi-way system with 4, 5, 6. I've seen some with 20 BA loudspeakers, which they sound good, but it's a lot of loudspeakers to put in a single device. With MEMS loudspeakers, this can be done. This is something that we do have in mind and working on, but it's not necessary. You can have a single MEMS loudspeaker go from we have a reference design where the loudspeaker goes from below 9 hertz up to 40 kilohertz before it does anything noteworthy.
Fantastic.
With a single loudspeaker.
All right. Well, that was about an hour and a bit on.
I've got one more thing.
All right.
Because I'm curious about this too. You mentioned the company was formed in 2014 and you got to production by 2018, kind of a thing.
Yeah.
That sounds pretty fast to me. Did the guys already have the designs ready when they started the company?
Not ready, but they, as said, they started thinking about the basic concepts earlier, started already reaching out to the foundries, reaching out to the manufacturing partners, and the first concepts were apparently already there when the incorporation, like the legal entity of the company, was formed, so they could start right away.
Yeah,
but it's still.
Our founders do have a big background in MEMS technology, so they have worked with ad companies together that did MEMS sensors in this case. So they have a large background in MEMS technology. They're absolutely not new to this. And when they came up with the idea of MEMS loudspeakers, it was just a couple of years before they incorporated the company. And when they started the company, they already had a prototype going. I was hired in 2015, so a year after that. And by that time, we had the second generation of working prototypes, and we're just figuring out the fine details. So it was relatively fast, but it was possible because they already had so much experience.
So I just imagine, I don't know the numbers, but the cycle time to actually develop a silicon and manufacture it is a pretty long time. Right? Is it half a year or more?
That depends on the foundry that you're working with. We don't have fixed cycle times because we don't adhere to all of traditional silicon processes because, it's in the end we have to work with acoustics as well. But yeah.
Awesome. Thanks very much.
Okay. All right. So Paul and Konstantin, and of course, always Simon, thank you guys very much for taking the time today. We will put all the links for your social media in the description below for everybody to check out for more information. And so, of course, everybody, the THD Party, if you like what we're doing, please like and subscribe and share this video. So, okay. Thanks, everybody. Have a great day.
Thank you very much. Have a good one.
Bye, everybody.